So the motivation for this work is essentially the observation that programs are multilingual. That even if you sort of write all your application code in one language, say language L, which I'll color blue, inevitably, probably you're linking against some foreign code. I'm coloring that in yellow here for the talk. Maybe that's a library, maybe that's some common code, maybe that's a runtime, but probably there's some other code. And at the same time, we care about type soundness. Type languages should be sound. It's at least something we aspire to in the type languages, even if we never prove it. And so typically, type soundness is proved via this pair of lemmas from Wright and Eliason called progress and preservation. And the reason why I want to highlight this is they rely upon the operational steps of your language. Right? The idea of progress and preservation is as you evaluate, you preserve the types. As you're running, you keep, the types are preserved, and so you never get stuck. And the problem with that is that you can't use the operational steps of your language to run foreign code. So at some point in running your code, if you were trying to use this approach, you transfer control to this foreign component, and you're stuck, right? There's nothing you can do. And so how do we resolve this? Well, one approach is to do basically what Jacob Matthews and Matthew Findler did and construct a multi-language. So basically their idea was, well, let's take the two languages, let's put them together, create a combined syntax, and we'll add what they call boundaries that mediate between the two languages. And the idea here is that if you have some term E from your blue language that has a type tau1, you can use it in a yellow context at type tau2 by wrapping inside one of these boundaries. And operationally, what this does is run E down to V, run the blue value, sort of running according to the blue rules maybe, and then translate that using this type-directed meta function to a yellow value, and then that reduces. And this works, and I mean, this was a paper that people have built a lot of things off of. But there's sort of a problem with it, which is that this reduction, if the languages are really different, this reduction is not necessarily the reduction from your blue language. So intuitively, you're saying, well, I'm taking my blue expression E and I'm running it down to a blue expression, blue value V, and then I'm translating it. But if you imagine that the blue language was pure and the yellow language has a heap, you can't sort of forget that a heap exists as you run that expression. And I mean, because the blue term E might have nested inside of it yellow code inside of an LF boundary, and that yellow code obviously needs a heap. And so you may have just inadvertently made your pure language stateful. And what you prove sound in this approach is this multi-language. So you've created this novel semantic artifact, and you've proved it sound, but there's sort of a question of how does that relate to the actual program you ran? How does that relate to sort of the notion of soundness that you wanted from the original types in your language? And so we sort of took a step back and we wanted to say, okay, can we connect this back to the actual programs? Can we try to connect to the programs themselves, not to this multi-language that is maybe something else? Because the reality is we don't run multi-language programs, right? You don't have an interpreter for this multi-language. What you do instead, normally, is you translate your application code and you translate the library, or maybe the library is already written in your target code, into some target or IR, and you run that resulting program, right? And this doesn't, maybe this is a low-level language, maybe this is x86 or LLVM or WebAssembly, or maybe if these are embedded DSLs, this could be a language like Racket or Haskell or Scala. But the point is, to run the program, you usually are going to get everything into this common sort of substrate and run there. And so that's the sort of context we want to take and say, how do we prove that sound? How do we prove it actually runs sound? Because soundness is about the running behavior of programs. And if we think about the boundaries, like there is usually some syntax that is used to mediate between the native code and the foreign code, whether that comes from an FFI library or it's built into your language, or maybe it's part of the embedded DSL framework or something. And that boundary code usually gets realized in some glue code in the target, right? Maybe that mediates between calling conventions or mediates between different value representations or whatever. So we want to account for all that and prove this sound. So how do we do that? Well, we essentially take an old idea of proving type soundness, which is semantic type soundness. And the proof approach, essentially, you say if a term is statically well typed, if E has type tau under an empty environment, then it should have the semantic type tau. And I'm using this double turnstile to mean semantically well typed. And that being semantically well typed should imply that it's sound. Usually that's just sort of built in. That step is usually pretty easy. And what I mean by semantically well typed, at least in our work, is that it belongs to a logical relation of that type. So the term E is in the expression relation. It is an expression that behaves like tau. And that expression relation in particular includes terms that are sound. So soundness is built into the notion of the expression relation. But there's a little bit more, and in particular, the first key part of our approach is that our logical relations are realizability models. And what do I mean by that? Is that we have a set of values. We have a value relation, which is typical for logical relations. We have an expression relation, set of expressions that behave like that type. But these are not values or expressions from our source language. So the set of values of type Boolean are not true and false. So that's what's in our source language L. They're target values, right? Here, maybe 0 and 1, if that's how we represent things. And the idea of using realizability models to prove type soundness has been done before. Nick Benton and collaborators had a couple papers about 15 years ago when they were doing this. But they were always doing this for single languages. And this idea really sort of, the power of it becomes apparent when you bring it into the context of interoperability. And what do I mean by that? Well, we index our relations by types from both languages, right? So we say we want to know all the set of values of type blue tau for all the blue taus and also all the yellow taus. And importantly, these sets are drawn from the same target language. And this is sort of the key insight to this work. If it's the only thing that you take away from it, this is it. Because this allows us to ask and answer really important questions for language interoperability. In particular, we can ask, is a type in one language equal to a type in the other language? So normally languages are sort of relatively non-compositional artifacts that are made up of a series of rules for static and dynamic semantics. And comparing them, I mean, you can say, well, maybe they're isomorphic, maybe you can translate between them. But here we can actually say, are these types identical? Because they're sets that are inhabited by the same values, the same expressions. And that's exactly the question that you want to ask when you're thinking about, as values flow across the boundary, the language boundary, what do you have to know for that to be safe? Well, in particular, if we're trying to use a foreign value of type tau2, yellow tau2, in a native context of blue type tau1, if those types are identical, we can just use that value. We don't have to do anything. But you can also ask questions, well, is one a subset of the other? In that case, maybe in one direction, we don't have to do anything. In the other direction, it's more complicated. Maybe you have to check something. Maybe you have to convert something. And more generally, we can actually ask, what kind of glue code, target level glue code, can be used to relate values or expressions from one language to the other, right? We can actually reason about the target level glue code. And so if we come back to the boundaries, sort of the key sort of point of interoperability, we reuse the same syntax, more or less, from the multi-language semantics. We separate out this type conversion. We say we want the relation between the types on both sides of the boundaries to be this declarative judgment, which we call convertibility. And the question is, how do we prove that sound? What does it mean for that to be sound in terms of how is it okay to use this term, E, the blue term of tau1, in a context that expects a yellow tau2? How do we know that's okay? And in particular, what target level code maybe do you need to insert to make that okay? And as I said at the beginning, one of the observations that sort of started this work was that conversions, target level conversions, glue code, inhabits that, it realizes that type level relationship. And so we can actually make that concrete by saying, well, this convertibility judgment is inhabited by two bits of code. It's a target level code. There's one that takes blue type tau1 code, turns it into yellow type tau2 code, and there's another that does the reverse, right? And for those to be sound, for those bits of code, these are target bits of code, right? For those bits of code to be sound, what we need to know is, well, if you give me any target level expression that behaves as a blue tau1, then if I wrap this glue code, if I wrap it around it, then it should behave like the yellow tau too, right? And the fact that we can do this is because this set and the glue code itself, it's all target code. We brought everything into this common environment, and the common environment also corresponds to how things are going to run, right? So our semantic framework lines up with also the programs that we care about. And so once we've done this, we can prove that, yes, the boundaries are actually correct, and then we can do sort of normal semantic type soundness work to prove that the single languages are correct, and we get that the whole system actually works. And so we've done this in the paper with 3 different case studies that account for 5 different source languages in total and 2 target languages. Our target languages are untyped, not only because that's sort of a realistic setting. Normally, target languages are untyped, or at least have weaker types than the source languages that they come from. And the point is, our models don't require that the inhabitants be typed, right? The model itself captures the structure of the types and allows us to sort of reason about the glue code that moves between sets. And so one of our case studies is about type-safe pointer exchange, and essentially that's like you have 2 languages that both have ML reference style pointers, like safe pointers, and how are you able to transfer them across without introducing proxies or things like that. And essentially what we show is you need the types that those point to be isomorphic, right? They need to be identical, not isomorphic, sorry. They need to be identical, because if you give someone a pointer, you may have an alias to it, and so you can't control what they write to it, and they can't control what you write to it, and so you better both accept all the possible values that can go in, or you're going to end up with unsoundness. The second case study has an affine language and unrestricted language, and we show that the normal approach of enforcing affine types dynamically, that works, and the glue code that sort of realizes that is all sound. And the last case study, which is maybe the most interesting, we have a garbage collected language, and we have a language with linear manual memory. It has linear capabilities for pointers. And we show that you can take memory from the linear manual heap and give it over to the garbage collected language, and that's safe. You don't have to copy. You can say, okay, this memory is now yours. The garbage collector can own it. And this is safe because the linear invariant means there can't be any aliases, right? And so the garbage collected language can now own this, right? And the other direction you can't do, but that direction is fine. And this is done even though our target languages are untyped, which means you've erased all these linear capabilities, but our models still show that the glue code does things correctly. So the key takeaways to this work is you can prove that sort of untyped target code, low-level IR code, satisfies semantic types, and that target code is a common substrate for interop. It's a really useful way to think about interoperability, and that really you should think about that glue code as maintaining type invariance. That's the point. It's trying to translate type notions from one language to the other language, and what we've done is sort of showed how can you actually do that. So I'm happy to take questions.
Hi, Daniel. Great work. A question. So the value relations looked like the realizers were essentially the sort of normal value specification for compiler correctness. How much does some sort of compiler-y notion end up showing up in the expression relations?
So your compiler has to satisfy the model, right? You have to compile terms into things that are in the model, but the model doesn't have to match your compiler. It can include more things. So, for example, actually in in some of the case studies in the paper, I don't actually represent Booleans that way. I represent Booleans as all numbers, because it's fine. The target language has an if0 construct, and it's actually okay if we allow everything non-zero as false, even though we only ever compiled with 0 and 1. And so there's a connection between the compiler, but you're not restricted to that. And that's actually useful because one thing you can do is prove arbitrary target code behaves like this type, right? Inhabits these semantic types, and as a result, it's safe to link. So you're not necessarily confined to using the source level compilers, though obviously you're then obligated to do manual proofs, which may be unreasonable. But I mean, that's sort of there's a way to see this work is you can view what, for example, the Rust Belt project did in this framing. In that case, maybe manually proving things does make sense, right? That they inhabit the semantic types.
Hey, great talk. Thank you. maybe this is a very simple question, but in your boundary semantics, you required a symmetric relation between the types. And I was wondering why it needs to be symmetric and why we can't do like, oh, it's safe to go this way, but not the other way.
So you don't need to make it symmetric. Basically, we did, it was how we set things up. And I think in some ways you may end up with confusing results because in the higher order case you flip. But the idea of the realizability models, the proofs you have to do doesn't really connect to the particular syntax you choose for your boundaries, right? And that's what the convertibility judgment is all about. It's like, how do you type check the boundaries? And if you just split that into two directed relations, everything else sort of falls in exactly the same way.
Hey, thank you. Following up on the compiler question, how does this relationship between the compiler and the expressor relation interact with the more conventional idea of compiler correctness in terms of refinement of operational semantics between the source and target language?
So we're not proving compiler correctness. We don't actually, in none of the cases we don't ever have source semantics. So there's nothing to preserve. We sort of took the approach that, well, in many cases, your semantics are defined by your implementation. So that's what we did. We said we have a compiler, we have semantics for our target, and that's what we're going to define, and we're trying to prove type soundness. Obviously, if you want to prove compiler correctness, you can reuse a lot of stuff because you're sort of building similar machinery, and there's no reason you couldn't do both. But we sort of wanted to separate this out because compiler correctness is in some ways harder, right? It's more work, and we didn't want to require that, right? And so we have no source semantics ever in the paper.
Right. I have a quick question. So I really like this insight about realizability and using a common target language as a substrate for this kind of reasoning. If the compiler and the libraries are third-party developed, it seems like things might not line up as cleanly. Have you thought about if there's sort of a recipe or some design insights that you would use to make this work well versus maybe anti-patterns where it's going to be a lot more work to come up with the glue code or to do the reasoning about the whole ensemble?
I mean, to some extent, one observation that if you start thinking about this, you probably are making is if you're looking at an actual compiler, current compiler, to a low-level target, the code is huge. And so the idea of sort of building your models on top of this code directly might be a lot of work. And to some extent, it's like, well, that's what you have to do right now. That's actually how, if you want safety, that's the code you have to think about, because that's what's done. But maybe the insight is, it would be nicer if we had higher level IRs where we actually were linking things together, where this were a little bit less onerous. And I think like an example of that is like the interface types project in WebAssembly, where they're trying to develop sort of a higher level common language of types. And if you then think about interaction at a level like that, which is a little higher, you have all the same obligations, but things become a lot easier than if you were like, if you're trying to do this for x86, I mean, good luck. But at the same time, it's like if you're trying to prove an existing FFI safe, that is the code you're dealing with, right? That's the code you have to reason about, and that you just are currently hoping is sound for some definition.
Great. All right, one more question. Great, we have time.
If you, following up on that sort of IR for rules, if you want to try to reason at as high a level as possible when doing, let's say, if you're trying to do proofs about your source programs, sort of, do you have sort of a path to making source language like reasoning facilities available? So, like, because right now you have to reason, if you're trying to, let's say, use these models to do proofs, you would have to do proofs about the target language, right?
Yeah, and I mean, I think one of the insights to this work is that like that is where interoperability usually happens, right? Because there is an extent where like if you have different languages that are genuinely different, you have to bring them together somehow. And even if your way of bringing them together is you implement an interpreter that then knows how to call this other code, your implementation of your interpreter is now in a lower level language, right? It's implementing your higher level language. And so you've moved down. And it's like you're always moving down to bring things together. So the observation is like, well, maybe we can make that moving down a little bit higher, but I think that you can't do interoperability without thinking about sort of common languages that you translate to.
All right, thanks.
Great. So we're at time now. So let's thank Daniel again.